Bismillahirrahmanirrahim. Hello everyone. This is the first method, which is called ADM decomposition method. We will call it ADM. Let's begin. I will explain the ADM decomposition method for solving linear Volterra integral equation. By giving the steps of the method briefly, and then I will explain it again in a detailed way. First, we let u of x equal to the summation n from 0 to infinity un of x, where u of x equal to u naught of x plus u1 of x, and so on. We substitute with the summation in the integral equation, and then we write the ADM decomposition recurrence relation as the following. We let u naught of x equal to the f of x, and we write un plus 1 of x equal to the lambda multiplied by the integration from 0 to x of k of x and t un of t dt, where n is greater than or equal to 0. Notice that u naught of x is all the terms that's not under the integral sign, and uj of x, where j is greater than or equal to 1, is calculated from the recurrence relation, which is un plus 1 equal to lambda, the integration from 0 to x k of x and t un of x d un of t dt. So we have u of x equal to f of x plus lambda, the integration from 0 to x to k of x and t ut dt by ADM. We write u of x equal to summation n from 0 to infinity un of x, which is mean u0 of x plus u1 of x, and so on. Now let's substitute here and here. Summation n equals 0 to infinity un of x equal f of x plus lambda, the integration from 0 to x k of x and t summation n equal from 0 to infinity u of t u sub n of t dt. Now let's expand those summations. U naught of x plus u1 x plus u2 of x, so on. F of x plus lambda, the integration from 0 to x k of x and t u naught of t dt. Now we have this summation is u naught plus u1 plus u2 plus and so on, and we know that the integration can be disturbed on terms that is added together, as we know. Can write it here. to make it more simple, integration of a plus b plus c is equal to the integration of a plus the integration of b plus the integration of c. This is in a simple form. Okay, so this is what we will do here. So lambda, the integration from 0 to x, k of x and t, u1 of t, dt, and so on. Okay, so we will take u naught as f of x, okay, which is the part that is not under any integral sign. Okay, and then we will take u1 as lambda, the integration from 0 to x, k of x and t, u naught of t dt. So we will write it like this. Sorry. Okay, and then u2 is this term. Okay, so u2 and so on, of course. u3 is going to be here, and then here is going to be u2. So this will lead us to the recurrence relation that we mentioned, which is u naught is equal to f of x and un plus 1 of x equal to lambda integration from 0 to x the integration from 0 to x k of x and t un of t dt, where n is greater than or equal to 1. Okay, so if we plug here n equals 0, so we get u1 with respect to the value of u naught, and so on, so we can get all the values of the terms in the summation. Therefore, we can get the value of u of x, the exact value of u of x. Okay, hope you understand. Now let's do the examples. I divided them into two groups. The first group, we will solve it together. The second group, you will try it yourself. All the equations are Volterra Integral Equation and linear, so we can use the method that I have explained. Here is our equation. Okay, first of all, what we will do, we will let x equal to summation n from 0 to infinity un of x. Okay, And then we will substitute in this equation with this summation. So summation from 0 to infinity un of x equal x plus the integration from 0 to x t minus x summation n from 0 to infinity un of t dt. So we can obtain our recurrence relation of the ADM where u0 of x equal to the f of x. Here f of x is equal to x and our recurrence relation is n plus un plus 1 of x equal to lambda here is equal to 1, so integration from 0 to x t minus x un of t dt. Okay, so we have u0 and we can use this recurrence relation to get more elements. Okay, and it's greater than or equal to 0. So we can get u1 of x when n equals 0. The integration from 0 to x t minus x u0 of t dt. Okay, and this will be equal to the integration from 0 to x t minus x t dt. Okay, so this will be equal to integration from 0 to x t squared minus xt dt, and then this will give us t raised to 3 over 3 minus x is a constant, so t raised to 2 over 2, and this is from 0 to x. This will be equal to minus x raised to 3 over 3 factorial. Okay, if we get the next element when n equal to 1, we can get u2 of x, which is going to be equal to the integration. Again, we are using this relation. The integration from 0 to x t minus x u1 of t dt. u1 is minus t raised to 3 over 3 factorial, so minus 1 over 3 factorial, the integration from 0 to x t raised to 4 minus x t raised to 3 dt. Okay, and then we will integrate and we will get t raised to 5 over 5 factorial. Oh, without factorial, I'm sorry. Minus x t raised to 4 over 4. Okay, and this is from 0 to x. This will give us x raised to 5 over 5 factorial. And then we now have 3 components. Let's see if we can really reach to the answer or not. U of x equal to u0 plus u1 plus u2 plus and so on. Our u0 is x, u1 is minus x raised to 3 over 3 factorial. Our u2 is x raised to 5 over 5 factorial, and so on. This can be written as a closed form, which is n from 0 to infinity minus 1 raised to n x raised to an odd number over 2n plus 1 factorial. And this is sine x. And this is our solution that we wanted to reach to. I hope you understand it. This is the second example. U of x equal 1 minus x minus the integration from 0 to x minus dut dt. Okay, we are using the ADM, atom and decomposition method. So our ux will be equal to the summation n from 0 to infinity un of x. So our recurrent relation for this method will be u0 of x equal to the f of x. Our f of x is 1 minus x in this example, so u0 equal 1 minus x, un plus 1 of x is equal to minus the integration from 0 to x minus t ut un of t dt, where n is greater than or equal to 0. Now let's get the value of u1 of x, where n is equal to 0 minus the integration from 0 to x minus t u0 of t dt, and this will be equal to minus the integration from 0 to x minus t 1 minus t dt. This will be equal to minus the integration from 0 to x minus xt minus t plus t square dt. Now let's do the integration. It's going to be minus xt plus xt square over 2 plus t square over 2 minus t raised to 3 over 3 from 0 to x. Okay, this will give us minus x squared plus x raised to 3 over 2 plus x raised to 2 over 2 minus x raised to 3 over 3. Now we have minus x squared and plus x squared over 2. This will give us minus x squared over 2. And we have x raised to 3 over 2 and minus x raised to 3 over 3. And this will give us plus x raised to 3 over 3 factorial, which is 6. Now we can get the second one when n equal 1. We can get u2 of x, the third one, and this will be equal to, remember we are substituting in here this recurrence relation, so we will have minus the integration from 0 to x minus t u1 of t. Our u1 of t is minus t squared over 2 plus t raised to 3 over 3 factorial dt. Okay, this will give us minus the integration from 0 to x minus xt squared over 2 plus xt raised to 3 over 3 factorial plus t raised to 3 over 2 minus t raised to 4 over 3 factorial dt. This will give us, let's integrate, so x t raised to 3 over 3 factorial minus x t raised to 4 over 4 factorial plus minus t raised to 4 over 4 multiplied by 2 minus t raised to 5 over 3 factorial multiplied by 5. And this is all from 0 to x. Okay, this will give us x raised to 4 over 3 factorial minus x raised to 5 over 4 factorial minus x raised to 4 over 4 multiplied by 2 minus x raised to 5 over 3 factorial multiplied by 5. Okay, when we simplify this, this will give us, we have here x raised to 4, okay, 1 over 3 factorial and minus 1 over 4 multiplied by 2. So we want them to have the same demonstrator, so we can subtract. So we will multiply by 4 up and down here, and here we will multiply by 3 up and down. Okay, and that will give us x raised to 4 over 4 factorial and for x raised to 5 we will multiply here up and down by 5 and here up and down by 4, and this will give us I forget this one, this should be plus, not minus, okay. I forget to put minus, multiply by minus to get plus here, so we will have 4 minus 5, which is minus x raised to 5 over 5 factorial, okay. So let's substitute in here u0 1 minus x, u1 minus x raised to 2 over 2 factorial plus x raised to 3 over 3 factorial plus u0 plus x raised to 4 over 4 factorial minus x raised to 5 over 5 factorial, and so on. So we have here, we can take the powers with even powers with even numbers, okay, and put them together. So we will have 1 minus x squared over 2 factorial plus x raised to 4 over 4 factorial, and so on, plus the odd ones are here. So we I want to put the minus outside, okay, so minus x raised to 3 over 3 factorial plus x raised to 5 over 5 factorial, and so on. Now this can be a closed form, which is summation n from 0 to infinity to minus 1 raised to n x raised to 2n over 2n factorial. And this too can be a summation in a closed form, which is n equals from 0 to infinity minus 1 raised to n, and the powers are odds, so 2n plus 1, and factorials are the same, so 2n plus 1 factorial. And this closed form is for the cosine, and this one is for the sine, and this is our ux, okay. This is our last example, u of x equals 3 plus quarter the integration from 0 to x plus t squared u of t dt, and this is the answer that we have to reach to. First of all, we of course are using the ADM method, so u of x will be equal to, according to the method, from 0 to infinity un of x, and our recurrence relation will be u0 of x equal to 3, and then un plus 1 of x will be equal to 1 over 4 the integration from 0 to x plus t squared un of t dt, where n is greater than or equal to 0, so we can obtain more elements, okay. N is equal to 0, u1 of x equal to 1 over 4 the integration from 0 to x plus t squared u naught of t dt, and this is equal to 3 over 4 because our u naught is 3, so we can get it out from 0 to x plus t squared dt, and this is equal to 3 over 4 x t plus x squared t raised to 3 over 3 factorial over 3 from 0 to x. Okay, 3 over 4 x squared, because we substitute with respect to t, plus x raised to 3 over 3. Okay, so we get 3 over 4 x squared plus x raised to 3 over 4, and these are the first 3 terms, okay, of u of x. We get them from u naught and u1, so we can write it like this: u of x is approximately equal to u naught of x plus u1 of x, which is equal to 3 plus 3 over 4 x squared plus x raised to 3 over 4.